Now we will see the concept of internal energy. What does it mean? So it is denoted by usually capital U or capital E. Fine. So it is defined as it is sum of the mathematical sum of internal kinetic energy and internal potential energy of a system. So since we are in the thermodynamic system, mostly we will have system as a gas. Okay, so you can define U as U kinetic energy plus U potential energy. So what does it mean? Suppose we are having a container, a cylinder of in which a gas is filled. So there must be some kinetic energy of the atoms of the gas, right? And also there must be some potential energy due to the interaction, the Coulombic interaction, right? And also the van der Waal interaction, the wall of the atom and the atom of the gas. So if we combine and the whole sum of that total energy is called the internal energy of that gas. Okay, so a few points about the internal energy you must be aware of. It is a state variable, and the moment I said it is a state variable, you must be careful that now all the properties of the state variable will be applied for the internal energy. And what are those properties? It is a state variable, meaning in a process, in a thermodynamic process, delta U. What do you mean by delta U? The change in the internal energy. Suppose there was a process that started from point A to point B, or the state A to state B. The internal energy, the change in the internal energy will not depend on the path. It will only depend on the initial and final position. That is the meaning of the state variable, right? So meaning in a thermodynamic process, delta U is path independent. Delta U depends only on initial and final states. Fine. And of course, what does it mean? If I show you by a graph, sorry, indicator diagram to be precise, and I take PV diagram. Now I start from state A and I reached at state B. I used three different paths. Path 1, then I used second path, path 2, okay, and then I used the third path like this. Okay, let's make it doesn't matter. Okay, so suppose this is the case. Let me label these three paths. This is first, this is second, this is third. So what does it mean? That delta U for path 1 delta u, and let me call it delta u1, okay, is equal to delta u2 for part 2 equal to delta u3 for the process, for the thermodynamic process going from taking place from A to B, or going from A to B, better to say process taking place from A to B. तो ये फर्क नहीं पड़ता कि कौन सा पाथ हमने लिया, दिस डेल्टा यू विल बी सेम. Now the next thing, again this is the property of state variable. For cyclic processes, the delta u will be 0, right? We have seen these things before. Now cyclic processes were two types of cyclic processes we have seen. This is that are the clockwise and anti-clockwise. So this will be 0 for cyclic processes. Let me again make it clear by a diagram. Suppose a process starts from here and it comes back to itself. Let's not make it circle. It start from here and then go for like to here. This process, or it can be like this, it start from point 2, state 2, and makes a rectangular path like this. So in all the cases, delta u1 equal to delta u2 equal to 0. So there should be no confusion in this case. It's too straightforward. One more important point about internal energy is that it is an additive quantity, right? It is an additive quantity. That is, you must have learned about the intensive and extensive quantity, right? That changes with volume and pressure. मीनिंग अगर एक सिस्टम की इंटरनल एनर्जी u1 है, दूसरे सिस्टम की इंटरनल एनर्जी u2 है, सो द u फाइनल दोनों का सम होगा लाइक दिस. सो दिस थिंग्स विल बी यूज्ड in later discussion. Fine. Now these were the key points. Key point 1, key point 2, no sorry, key point 2, 3. Let me denote them by numbering. Let's call it 1 like this. Let's call it 2 and 3. So if you see the definition of the internal energy, we said that U equal to U kinetic energy plus U potential energy, but it is for in general for any kind of gas. Now we come to the ideal gas, because we have said in the last lecture that ideal gas is very special gas and we want to study it for different purposes. So for ideal gas, U potential energy is 0, meaning there is no interaction between the atoms of the gas. So hence U potential energy is 0, means internal energy is just kinetic energy of the particles of the gas. This is the special case. Now few more terminologies. You must have heard about the heat capacity, right? See, it is the amount of heat required to increase the temperature of any material or any sample of the sample of a material by 1 degree Celsius or 1 degree Kelvin, doesn't matter, but not Fahrenheit. It's called heat capacity. Okay, and its unit is, of course, you can guess, that is calorie per Kelvin or calorie per degree Celsius. The formula you can write like C equals dq by dt or delta q by delta t. Fine. And remember, if you have a situation in future, then you can write infinitesimal change of heat dq. You can write it as C times dt. So you can you must be aware of these things. If we use it further, you don't have to surprise कि ये कहाँ से आया. Now the next is specific. And the next similar point is the specific heat. It is the amount of heat required to increase the temperature of unit mass of a sample of material by 1 degree Celsius or 1 degree Kelvin. So that is called specific heat capacity. So you just have to add this thing, unit mass, in the previous definition. Of course, the unit will be calorie per Kelvin, kg per Kelvin, like this, or not degree, or calorie per kg degree Celsius, like this. And it doesn't have to be calorie, it can be joule also, because you know the calorie and joule, heat and work and heat. 1 calorie equal to 4.18 joule. Okay, so this is the specific heat. But suppose, since we are saying that the amount of heat required to increase the temperature of unit mass, but now we are giving the heat in a specific way in a particular way. Okay, so now it has two special cases. The first one is if the volume of the sample of the material is kept fixed. ओके, मीनिंग हमारे पास एक मटेरियल था जो गैस, मान लो मटेरियल को छोड़ दो, ज़रूरी नहीं कि गैस ही हो, बट फॉर एग्जांपल, एंड इसमें हमने ऊपर से इट इज़ पैक्ड, इसका हमने यहाँ ऊपर से लिड लगा रखी है. नाउ वी आर ट्राइंग टू हीट इट. Okay, we are trying to heat it, but the volume is fixed. In this case, now what amount of heat I will require to increase the temperature by 1 degree Celsius of the 1 kg of gas or 1 unit mass of the gas? The volume is fixed. So in this case, this is called, I mean the definition is slightly this is known as, if the volume of the sample of the material is kept fixed, this is called specific heat at constant volume. Okay, and earlier I have forgot to mention one more thing, that since the formula will be what here, dq equal to C equal to dq by dt, but divided by mass. Now since the volume is kept fixed, now we need to use this v in the subscript cv and 1 upon m dq by dt, but you have to mention in here also, because you will see this is the in partial derivative, you will see that this will be used, so better to use the partial derivative. del Q by del T at constant volume. Okay, so this is the first case. The second case is if the pressure is kept fixed. If the pressure of the gas is kept fixed, just change the volume by pressure. If the pressure of the sample of a material is kept fixed, then the specific heat is called the specific heat at constant pressure. Then you have to change the subscript by V to P. Okay, and here also P pressure, so that you can remember that it is the specific heat at constant pressure. And how this case will be, right now the gas is there, but there is nothing is closing the system. There is only environmental pressure, the ATM, right? And we are heating it from beneath. नीचे से हम इसको हीट कर रहे हैं तो प्रेशर इज फिक्स्ड, देयर इज नो एक्सटर्नल प्रेशर. सो दिस इज द केस व्हेन द स्पेसिफिक हीट एट कांस्टेंट pressure will be used. And now you can see that since dq or the C equal to 1 upon m dq by dt, from here you can write the dq is equal to C times m dt. Okay, and if I integrate it, I can find out the total heat. If I integrate it, I can find the total heat in the process. And suppose the gas is the process is something that the volume is fixed, volume of the gas is fixed, then what I will use dq equal to cv m dt. And if the pressure is fixed, then I will use dq equal to cp m dt. So these will be used in later. So in general we'll use C, but if the process is kept in constant pressure or constant volume, that C will be used like Cp or Cv according to the situation. Okay, so for heat capacity we are using C prime here, and for the specific heat we are using C. And one more thing comes here, that is if the mass, because we have seen that for specific heat we have this thing, right, for per unit mass. For per unit mass, the definition of specific heat and the heat capacity changes just by the per unit mass. Suppose we are not dealing with per unit mass, suppose we are talking about per unit mole, right, per unit mole. Then in that case the heat capacity will be changed to molar heat capacity. Okay, so the definition will be what? You can write the definition here also. You can just copy paste and change the unit mass to the unit volume, unit mole. Too simple, nothing complicated here. But this thing, read it. The amount of heat required to increase the temperature of 1 mole of the sample of the material, okay, called molar heat capacity or molar specific heat. Some other names can be used. Molar heat capacity or molar specific heat. Okay, and one more thing is mainly used in the books or in the processes. If the amount is used not in terms of mole but in terms of molecules, okay, so then in that case it is called molecular specific heat or molecular heat capacity. Okay, molecular. So now you can guess what will be here. The 1 per atom, 1 atom like this, or 1 molecule, or it depends on the what kind of gas it is. Okay, 1 atom. or molecule. Fine. So I think it is clear now, and the formula will change like this. This thing C, or you can define, you can give it the name it like this, Cn, that is 1 upon number of moles dq by dt, and this one C maybe capital M, like this, then 1 upon n dq by dt. Here n is number of molecules, here n is number of moles. Fine. So these were the all possible cases. So let me rewind it in, or make it summarize in very quick way. So the most general is heat capacity, C prime. If we are dealing with per unit mass, then it is heat capacity. If we are dealing with per unit mole, then it is Cn, molar heat capacity. If we are dealing with per unit atom or molecule, then it is molar, not molecular heat capacity, Cn. But heat specific heat capacity has two different variant. One is Cp, one is Cv. If the pressure of the gas is kept fixed, that is Cp. If the volume is kept fixed, that is Cv. So this is the whole mind map. Also remember that this Cp and Cv, this can be used for any kind of specific heat. We have seen that we are having mainly three types of specific heat. That is specific heat when we are talking about unit mass, when we are talking about unit amount, the unit mole or the unit molecule. सो ये Cp और Cv किसी भी केस में यूज हो सकते हैं, ध्यान देना, क्योंकि ये तो हमारे ऊपर है ना कि हम सिस्टम को कैसे हीट करना चाह रहे हैं. वी वांट टू हीट इट एट कांस्टेंट प्रेशर और वी वांट टू हीट इट एट कांस्टेंट वॉल्यूम. ओके, सो द मीनिंग इज दैट कि अगर मुझे लिखना है कि इफ़ आई एम ट्राइंग टू हीट माई सिस्टम और द सिस्टम इज़ ओनली 1 kilogram, that is 1 unit of mass, then in that case I will write this dq equal, because the specific heat is C equal to 1 upon m dq by dt. Okay, then I can write it as dq equals mc dt. Fine. Okay, this is one case. And if I want to heat my system at the system is at fixed number of moles, so I want to the system is defined as the per unit mole, then it will be C equal to 1 upon 80 means pressure, time नहीं है यहाँ पर, temperature है, dq by dt, and similarly it can be 1 upon n dq by dt. Okay, so ये जो यहाँ पर m आ रहा है, n आ रहा है और कैपिटल n आ रहा है, ये किसकी प्रॉपर्टी है? ये ऑथर तो मतलब ये सिस्टम की प्रॉपर्टी है, लेकिन तुम्हें क्वेश्चनर बोलेगा कि इन्फॉर्मेशन क्या पता है. मान लो मेरे पास एक कंटेनर था, ठीक है, इस कंटेनर में गैस भरी हुई है. अब मुझे इस गैस का मास पता हो सकता है, इसके नंबर ऑफ मोल पता हो सकते हैं, इसके नंबर ऑफ मॉलिक्यूल पता हो सकता है, कुछ भी पता हो सकता है. अब डिपेंड करता है कि जो सामने वाला तुम्हें इन्फॉर्मेशन कौन सी इन्फॉर्मेशन दे रहा है. क्या वो तुम्हें मास की इन्फॉर्मेशन दे रहा है, क्या वो नंबर ऑफ मोल्स की इन्फॉर्मेशन दे रहा है, क्या वो नंबर ऑफ पार्टिकल्स की इन्फॉर्मेशन दे रहा है. सो दिस इज द पॉसिबल वेज. नाउ इन एवरी केस वी कैन हीट द सिस्टम. अब तो हमें हीट करना है ना, सिस्टम दे दिया एक बार, अब सिस्टम इन तीन तरीकों से दिया जा सकता है. नाउ वी आर ट्राइंग टू हीट इट. अब हीट भी तो दो तरीके से किया जा सकता है ना, कि या तो हम कांस्टेंट प्रेशर में हीट करें या कांस्टेंट वॉल्यूम ऑफ द गैस में हीट करें. तो जो कॉन्सेप्ट ऑफ Cp है और जो Cv है, दैट विल बी कॉमन इन द ऑल केसेस. यहाँ पर भी Cp लिखा जा सकता है, यहाँ पर भी Cv लिखा जा सकता है. सो दिस विल बी 1 upon m dq by dt at constant pressure. Same thing will be written here and same thing will be written here. बट जस्ट चेंज द लेबल. मास की जगह पर यहाँ पर नंबर ऑफ मोल्स आ जाएंगे, यहाँ पर नंबर ऑफ पार्टिकल्स आ जाएंगे. सिमिलरली हियर द CV विल बी 1/m dq/dt at constant volume. Same thing, you can paste it here, but just the specification will be changed of the amount now is number of particles. So इस तरीके से करना होता है. ये कंफ्यूज करता है बहुत बार, क्योंकि कभी कुछ दे बोल दिया जाता है, कभी कुछ बोल दिया जाता है. सो दिस इज स्पेसिफिक हीट, जस्ट स्पेसिफिक हीट बोला जाता है. इसको बोला जाता है मोलर स्पेसिफिक हीट, एंड दिस इज मॉलिक्यूलर specific heat. Fine, now I think this confusion is clear. So if we come back to the internal energy thing about the ideal gas, so remember we are still talking about ideal gas. So change in the internal energy of ideal gas, that is delta U. Delta U is given by NCV delta T, or du equals NCV dt. D is used for the infinitesimal, and the delta is used for the not when the change is not infinitesimal. And you should remember what is the meaning of N here, number of moles. CV is the specific heat at constant volume. Remember this V is subscript, like this, because it is written here because of to remember that it is at constant volume. And delta T is here change in the temperature. So this is the internal energy formula for ideal gas. We will see how it is, how in later maybe I can derive it, but right now, as of now, you need to take it as a granted. But remember that this is okay. Let me write it. It is very important. This formula is valid only and only for ideal gas. First thing. Second thing, doesn't matter under which process the system is going, the system is passing or going. I mean isothermal, isochoric, isobaric, adiabatic, anything. Isothermal, isobaric, etc. कोई भी प्रोसेस हो, फर्क नहीं पड़ता. This formula is still valid. तो ओनली कंडीशन क्या है कि द गैस हैज़ टू बी आइडियल. अगर गैस आइडियल हो गई, ये पता लग गया, देन यू कैन यूज दिस फॉर्मूला blindly. You don't have to think anything else about. Okay, this is the thing here. So right here, condition is, or the only condition is ideal gas. Ideal gas होते ही you can find out this change in the internal energy of the system.